So I'd like to thank the organizers for the opportunity to talk at the summer school. My title is Topological Free Entropy, as you can see. There are many things about von Neumann algebras and entropy in free probabilities, two notions of entropy, the free entropies I introduced. I have also some not so recent work about C-star algebras instead of von Neumann algebras. This work has not been getting perhaps so much attention as the one with von Neumann algebras. And this is what I'd like to talk about, the connection with C-star algebras, free entropy that goes with C-star algebras. That's the topological free entropy. So it's an idea which resembles a bit also what happens with dynamical entropy. You know, if you have automorphism of compact metric space, then if there is an invariant measure, if you have an invariant measure, you have entropy from the measures, the Kolmogorov-Sinai entropy, but there is also the topological entropy of the topological dynamical system. Yeah? It's a bit a similar situation here. So the idea to define this topological free entropy is to use matricial microstates, microstates which are controlled by norms. Yeah, so the approximating non-commutative moments are replaced by norms. Instead of one controls the norms, approximation is concerns the norms, and this has connections with largest eigenvalue or norm facts for random matrices, that is results about norms. For random matrices have applications to this kind of questions about topological free entropy. And the topological free entropy, topological means that it's C-star algebraic. The von Neumann algebras are the non-commutative measure spaces, and the C-star algebras are the non-commutative topological spaces, if you want. So that's the reason why it's called topological free entropy. And my not so recent paper about that is in Letters in Mathematical Physics, this little paper in 2002. There are a lot of questions, and I'm going to present also a number of questions. So explain a little how this works, the definition of the free entropy, of the topological free entropy, and then also some of the questions. But first, because it's an analogy, let me remind how the free entropy, the usual one, the microstates free entropy, is defined in the von Neumann algebra context, so the non-topological things. So I'm having here M, a von Neumann algebra, and tau, a trace state, and I'm having an n-tuple of self-adjoint elements. Xj are self-adjoint, an n-tuple, j goes from 1 to n, elements in a von Neumann algebra, which has a faithful normal trace state, tau. Can think of a 2-1 factor if you want. And then there are the matricial approximants, the microstates. It's this set. So there is a number here, K, which gives the size of the matrices. There is M and epsilon, which are parameters which gives a degree of approximation. So if I'm having this n tuple n, I want it to be approximated in non-commutative distribution by an n tuple of self-adjoint matrices A1, AN of size K by K, yeah? These are the K by K matrices. It's an n tuple. And the approximation is in distribution, that is the trace tau of monomials, xi1, xip, monomials of degree up to m, is approximated by the traces. Here it's a normalized trace for the K by K matrices of the corresponding monomial. So here is AI1, AIP less than epsilon. You see, instead of monomials, I could have put, if you want, some non-commutative polynomials or things like that, and somehow these spaces are all related. It's much the same type of approximation. And then the free entropy is defined in the following way. It's a limit, a normalized limit of the logarithm of the volume of these microstate spaces. So taking these approximants, these microstates which approximate x1, xn in distribution, and I take their volume. The volume is with respect to the Hilbert space structure on the matrices coming from the Hilbert-Schmidt model. And it's the log of the volume, and one divides by k square, and there is also this additive correction here, n to logarithm of k, and one takes the lim sup as k goes to infinity. That's the first thing one does. And then one takes infimums after epsilon and after m. So these spaces of microstates become smaller and smaller when the approximation is improved. And one takes the inf of what one gets in this approximation. All this is an imitation of the basic thing from statistical mechanics of Boltzmann, that the entropy is logarithm of volume of microstates. Yeah, and the quantity one gets, it's chi of x1, xn. That's the usual definition of the microstates free entropy. And the idea to go over to topological is to replace this this microstate space, this defined in this way, by a microstate space where instead of moments one uses norms. And this is done as follows. One has now, instead of the von Neumann algebra M, there is a C-star algebra, unital C-star algebra A, an n tuple of self-adjoint elements A1, AN, and the microstates with various degrees of approximation are defined in this way. This gamma topological A1, AN, K, epsilon, P1, PM. Here, K is again the size of the matrices as before. Epsilon is a positive number, gives distance. And instead of moments, one has P1, PM polynomials, non-commutative polynomials in indeterminates x1, xn. And then the approximation is in the following sense. One has that the norms, so C1, Cn, such an n-tuple of K by K self-adjoint matrices, is an approximate in norm of A1, An, if these non-commutative polynomials Pj of C1, Cn have norms close to the polynomials in A1, An. Yeah, so one takes these polynomials, non-commutative polynomial, plugs in A1, An, and plugs in C1, Cn, and the two norms should be within epsilon. I should make here a comment. I mean, one could do the same thing instead of taking not all polynomials, taking matrices with polynomial entries. Yeah, so one could fix, say, P by P matrices, and with the entries, the matrices are polynomials, and then one plugs in C1, Cn or A1, An and puts a degree of approximation. It's the same concept. It doesn't lead to something different, because one can always control norms of matrices in this way by, if one has control over the norms of the polynomials of the entries. So ultimately, there is no gain in putting matrices instead of polynomials. Polynomial matrices, there is no gain. It's the same concept. And then one performs the same steps. One takes the logarithm of the volume of the microstate space, divides it by k squared, that's the dimension of the metric space, and one makes this additive correction n over 2 logarithm of k, and takes then infimum over all possible choices of epsilon, of m, p1, pm, the polynomials, etc. And that's the notion of topological free entropy. Yeah, so it's absolutely an imitation, but the microstates are now with respect to a norm approximation, not to approximation of the moments of the distribution. It's a norm distribution, if you want. And then here are a few properties of this quantity. One is subadditivity. If I'm having an n plus m tuple of elements in the C-star algebra, A1, An, B1, Bm, then the topological free entropy of the n plus m tuple is less than or equal the topological free entropies of the n tuple plus that of the m tuple, the a's and the b's. Yeah. Then there is another property of semi-continuity. The semi-continuity, there is such a property also for the usual entropy, and there you have that if you have distributions, if you have n tuples, distributions converge in the sense of moments, then you have a limb sup inequality for the entropies. You have here the same thing, but instead of convergence in distributions, there is a convergence of norm distributions. That is the limit of the norms of this poly. You have A1, An, n tuple with an upper index P. Yeah, in some C-star algebra, also an upper index P. And these converge in norm distributions. The norms of these polynomials, of non-commutative polynomials in the APs, converge to the norms of the polynomials in A1, An. Then the limb sup of the topological free entropy for the MPs is less than or equal the topological free entropy for A1, An. Yeah, has this upper semi-continuity if one has convergence in norm distributions. Then there is a result about what have an inequality for the change of variable. Here, what one does, one has this A1, AN elements in a C-star algebra, and the C-star algebra A, and one has to take functions of A1, AN. So what one does, functions will be non-commutative power series in n variables. F1, Fn is a non-commutative power series in n variables, and it has to satisfy the following assumption, that there is another n tuple of non-commutative power series, G1, Gn, which has good convergence properties, which is the inverse. So it's an it's a change of variable, if you want, which is invertible, a change of the n tuple of variables A1, AN to F1 of A1, AN, Fn A1, AN, but which is invertible. If you apply the G's, you get back to A1, AN, and they all have sufficient convergence that all these operations should make sense. So it's for good changes of variables from a convergence point of view. And then the topological free entropy after the change of variables. So I'm making, instead of A1, AN, I'm putting F1 of A1, AN and F up to Fn A1, AN, is bounded by the topological free entropy of A1, AN plus n times the logarithm of the norm of the differential of the Jacobian of the coordinate change. Namely, this is delta twiddle F, and it is an n by n matrix, and in the entries it's like a Jacobian. It's dfi over dai, if you want. The only thing is that when you take the derivative in the non-commutative polynomial, you put a tensor. So instead, yeah, that's if you see an aj, if you have aj, etc., then the aj, and you take derivative with respect to aj, you replace it by a tensor. Yeah, you see what was before, what's after, and you put a tensor. It's the derivation which takes the aj to 1 tensor 1. And so it's the same thing like we do a Jacobian matrix. Only if you get in this way an element in the n by n matrices with entries in the C-star algebra A tensor A opposite, the tensor product being the spatial tensor product of C-star algebras. And then one takes the norm of this differential Jacobian, as you want to call it. So the topological free entropy of after change of variable is bounded by the initial 1 plus n times the logarithm of the norm of the Jacobian. And there is another quantity with which this should be compared. It's like in the situation of dynamical entropies. When you have automorphisms of homeomorphisms, these are the automorphisms of metric, compact metric spaces, then the topological entropy is equal there to the supremum of all the Kolmogorov-Sinai entropies for invariant measures on the space. Yeah? And here one is tempted to find something similar, only one is not so lucky at this time to know that the two things are equal, but one has the two quantities and one must compare them. So there is this competing quantity, which I'm calling free capacity. You'll see in a moment why I called it capacity. Well, I use capacities, looking for a good name. I found capacity. So I'm having these n tuples A1, AN, which generate A, these self-adjoint elements. And then K of A1, AN is the supremum of the free entropies, the microstates free entropies, the ones which are for Neumann algebras, of A1 tau, AN tau, where A1 tau, AN tau are the operators one gets from A1, AN when one takes the representation associated with the trace state tau. So I have a trace state tau, one represents A using this, using Gelfand-Naimark-Siegel construction, and one gets a von Neumann algebra, and A1 tau, AN tau are the elements in that von Neumann algebra, which has, of course, a trace state. And the free entropy of this n tuple in a von Neumann algebra with trace state is chi of A1 tau, AN tau. One takes the supremum of all these over all trace states. This is the free capacity. It's the quantity is subadditive again. I mean, I have A1, AN, B1, BM. It's puts them together. It's a sum of the two. For the change of variable, the situation is one has something which is better. Instead of the norm of this Jacobian delta d twiddle f, one has the logarithm of the Cadison-Fugler determinant of this Jacobian. So this delta d twiddle f is an element, an n by n matrix with entries in A tensor A opposite. Yeah, this is a algebra which has a natural trace. It is a trace tensor, the tau tensor tau opposite, if you want. So it's a have a trace on the n by n matrix, is a trace on A trace on A opposite, and the tensor of this gives a trace on the n by n matrices with entries in A tensor A opposite. Then this Jacobian matrix has a Cadison-Fugler determinant. Yeah, so you take the absolute value of the matrix, yeah, it's matrix times star square root, and then take the logarithm and the trace of this. You exponentiate it afterwards. That's a Cadison-Fugler positive determinant. And here one has the logarithm of this Cadison-Fugler positive determinant. So the inequality is this, that that's the free capacity for after the change of variable is bounded by the initial free capacity plus the supremum of this overall trace states of the logarithms of the Cadison-Fugler determinants of the change of value. Now, here is the reason why I use the name of free capacity for this. In the case n equal 1, n equal 1, and if a one can then assume it's commutative, one has one variable only. It's just one self-adjoint element. You can take the C-star algebra to be the continuous functions on the spectrum of the element A. It's a lowercase a. I made very mistake in the, yeah, here is a lowercase a, not upper a. And then if I have a trace state on this, the trace state is a measure, or probability measure on the spectrum of A. And the entropy, the free entropy of A tau is just up to a certain constant theta, is minus the logarithmic energy of this measure. Yeah. So a trace is a measure, a probability measure on the spectrum. And this probability measure on the spectrum has a logarithmic energy, which is minus this double integral logarithm s absolute value s minus t d mu s d mu t. So here it's one changes the sign and adds a constant. Usually the logarithmic capacity is defined with an exponentiation. So it's this, this quantity you see here, subtracto, but and exponentiate. Yeah, that's the usual. But you see, it's in essence, the exponentiation can be undone. It's the same information. And that's the reason I use the name of capacity. Because in the case n equal 1, it has really to do with the capacity, logarithmic capacity. And the big question is whether the free capacity is equal to the topological free entropy. Here one has to make, of course, a certain assumption. I cannot expect it to work in absolute generality. I mean, for this free capacity to work, one needs an assumption that the C-star algebra A should have the trace states, should have enough trace states, and the C-star algebra one generates it by A1, AN, one doesn't go to a larger C-star algebra because then it's even more difficult to get trace states. So one assumes A is generated by A1, AN, and let's say has sufficient trace states in some sense that they should give some faithful representation or other conditions on trace states that there should be enough. Well, fortunately, there is something one can say. I mean, the equality would be too much to hope at this moment and hope that we can prove it. I mean, equality in full generality. But in full generality, one has one inequality, namely the topological free entropy is less than or equal this free capacity K of A1 AN. And I should give you a few examples. One is the example with in the semicircular case, semicircular variables. These are the analog of Gaussian variables in free probability. The way to, if you don't know what they are, semicircular elements, here is a simple way to define them. Take the full Fock space of Boltzmann. Yeah, so you take vector Hilbert space. You take H that direct sum its tensor powers, including the zeroth tensor power, which is C times 1, and then you take left creation operators, and these are the self-adjoint part of these left creation operators, and the left creation operators were self-adjoint parts. So that are the semicircular system. If you use the state which comes from the vacuum state for this Boltzmann Fock space. But of course, since here I'm not using traces, I'm using only C-star algebras, I can overlook the vacuum trace state, and just think of them as self-adjoint, as a self-adjoint part of these creation operators. So in the case n equal 1, what you have so if you have one semicircular element, this is the following. You have the unilateral shift operator in little l2 of the natural numbers. And if S is, if you have the shift operator, then it's the shift plus its adjoint divided by 2. That's a semicircular element. Yeah, of course, you can also multiply them with constant dilation. So it's a self-adjoint part of a unilateral shift operator. That's a semicircular element, one of them. An n-tuple, you have to do it in a free product way to get the semicircular system. And then one thing which one can prove is that the topological free entropy of an n-tuple, S1, Sn, is equal to its free capacity, and is actually also equal to the free entropy of S1, Sn, of the semicircle. So all these things are equal. The topological free entropy, the free capacity, and the free entropy. I write the free entropy because there is actually one has a unique trace states of the equality between free capacity and free entropy is obvious. And the essential ingredient here to prove this is one needs such normal microstates, and an essential way is to use the results of Hagerup-Thorbjørnsen about norms of polynomials, non-commutative polynomials in independent Gaussian random matrices. What they proved that you have this, that you have take such a non-commutative polynomial, and then you take here an n-tuple of self-adjoint Gaussian matrices with everything Gaussian in it. Then you have almost surely that the norms of the polynomials converge to the polynomial in the semicircular system. Yeah, Hermitian Gaussian. It is a vast generalization of the random matrix results about almost sure convergence of the largest eigenvalue of a Gaussian random matrix. That's, if you put polynomials and norms, it's a vast generalization of this. And this, there has been further work on this, I mean, of Hagerup-Thorbjørnsen, Mike Capitaine, Donati Martin, Camille Mal, Collins, Bordenave, and their work on going further about this. I think Benoit Collins will actually have one of the courses about such questions with norms of these random methods. I think this work is very relevant to extending, to getting results about immediate consequences about topological free entropy. Another situation is universal n-tuple of Hermitian contractions. So one takes here A is a full free product of the continuous functions on the interval -1, 1. And Tj is a jth copy of the continuous functions, the jth copy of the coordinate function in jth copy not of the C-star algebra. It's identical function in, yeah, it's identical function in the jth copies of continuous function of -1. So if you want, what is this? It is the universal C-star algebra generated by n self-adjoint operators of norm 1. Yeah, if I have T1, Tn self-adjoint operators of norm 1, there is a universal C-star algebra, the C-star algebra where the norm of a polynomial in this is the largest one can get for any choice. Yeah, and then every other C-star algebra generated by an n-tuple of self-adjoint operators of norm 1 all is a quotient of this. Yeah. So the topological free entropy of T1, Tn of this universal n-tuple is equal to its free capacity, and the free capacity is a free entropy in the case of a certain particular distribution. Namely, here what one takes is one looks it's what would be a free situation, and it has to do for one variable. One has to use the equilibrium measure on minus 1, 1. Remember the free entropy in the case of one Hermitian element is essentially a logarithm minus a logarithmic energy. This one is maximized by the arc-sign law. If one has the arc-sign distribution on the set minus 1, 1, the maximum one attains for this free entropy is for the arc-sign measure, arc-sign distribution. And here, so if one takes for each such variable an arc-sign distribution and in the free position, the most general position, then one gets the topological free entropy of T1, Tn. And this has another more general aspect, namely, when one defines this free capacity of A1, An, one takes free entropies of n tuples with respect to certain trace states. Now, there exists such a trace state for which one gets the maximum, for which the maximum is attained. This follows from semi-continuity properties of the free entropy. So there is such a, and in case I forgot to write here that n should be larger than 1. I mean, if n is larger than 1, then by the properties of, so starting with 2, for 1, it's of course, we are in the commutative case, but for n larger than 1, then this state where you have the maximum free entropy must be a factor state. Yeah, the representation must be a factor, no center. And it is natural to call such a state where the free entropy gets maximal, to call it a free equilibrium trace state. Only it's there is nothing, I think, which prevents from having several free equilibrium trace states. So the trace states for which the entropy, free entropy gets maximum exist, but I don't know that they should be unique. It's possible that there may be several. I have no unique. I should make another remark, is that if you look in my little paper, there is the notion used there is slightly more, has a technical additional complication. It is this topological free entropy of A1, An, and here you have also B1, Bm it's in the presence of B1, Bm. What that this means, it means that one has something larger, one has an n plus m tuple, and one takes those norm microstates of A1, An, which have extensions to norm microstates of A1, An, B1, Bm. Yeah, so there's a projection of a larger microstate space. Another thing I should mention, playing with definitions, is that there is a notion of semi-microstates. I put them here, semi-norm microstates. I put gamma topological, and I put here a 1/2 of this. And instead of assuming that the norm of the polynomial in A1, An and the polynomial in the microstate C1, Cn, the norms are within epsilon, one requires only an inequality. One will require that the norm of the polynomial in C1, Cn should be less than the norm of the polynomial in A1, An plus epsilon. This is a semi-microstate. Now, this one would think that the semi-microstates are more than the microstates because one requires less. So one has clearly this inequality, the topological 1/2. The topological free entropy with semi-microstates is larger than the one with simply topological. But here comes the analog of the cone conjecture, yeah, the cone embedding conjecture. There is a norm analog of the cone conjecture for C-star algebras. It has to this has another name. It has the name of something has to do with MF algebras in the Blackadar-Kirchberg sense. And what it is, I mean, the cone conjecture is equivalent to the fact that if you have elements in a von Neumann algebra with a trace state, then the microstate space is microstate space with respect to distributions to moments is non-empty for all degrees of approximation. And the norm analog of this, which has been considered by Blackadar, Kirchberg, etc., is that you put norm microstates in essence. It's the same thing. If you take norm microstates, you require that the norm microstates be non-empty. So if this condition is satisfied, then the free entropy with semi-microstates is topological free entropy with semi-microstates is equal to the one, the topological. Okay, now one of the dreams with free entropy is that with free entropy in the usual sense, one would be able to distinguish von Neumann algebra, that it should be one has properties which distinguish, but that one should be able to compute something. For instance, if you have a free group factor, one should be able to get the number n out of this, and this would have great consequences. And all this goes through the notion of free entropy dimension. Yeah. So there is a notion of free entropy dimension, which I introduced in the von Neumann algebra context. It's some idea of like the Minkowski content quantity derived from the definition of free entropy. On this microstate spaces, one takes something like a Minkowski content. And Ken Lee Jung has found a very useful equivalent definition. It's the same quantity he gets, but it's by a quite different construction. Namely, it uses epsilon nets, and this definition with epsilon nets I found it easier to use to define the analog of the free entropy dimension for the norm microstate setting, the topological. So there is a topological free entropy dimension notion, and it goes like that, the definition. First, some notation. If X is a metric space and epsilon is positive, n epsilon of X is the minimum number of points in an epsilon net of X, yeah? So it's the smallest number of points in X, such that every other point is within distance less than epsilon of one of these points. Yeah, the smallest such epsilon net. And then to define the free entropy dimension, in this case, in the topological setting, a la Kenley-Jung definition, is to do the following thing. One takes here this gamma top A1, AN, etc. So these are norm microstates of A1, AN with these K by K matrices, and the degree of approximation is with the parameter epsilon, P1, PM, P1, PM being polynomials. And so one takes, instead of the volume which was appearing there in the definition of the topological free entropy, one puts here these things with epsilon nets. When one takes, again, such a limit, dividing by k squared, and then one takes the infimum of these limits by overall choices of parameters. Yeah, so one takes more polynomials and any kind of polynomials, and if one takes the inf over all this, one gets this d epsilon A1 AN. And now the topological free entropy dimension is superior limit, epsilon goes to 0, of d epsilon A1 AN divided by the absolute value of the logarithm of epsilon. Yeah, taking the logarithm of epsilon. That's the free entropy, topological free entropy dimension. And there is a competing quantity, which is done like the capacity idea. Namely, one takes the supremum of these free entropy dimensions of A1 tau, AN tau. So one takes a trace state over A, one represents A1 AN in a von Neumann algebra, it has now a trace state. One takes the free entropy dimension there, and one takes does the supremum over all these trace states. And here one uses a little technical modification. I won't overuse it. It's delta naught, called modified free entropy dimension. And examples, for instance, of such situations is that the topological free entropy, if it's finite, so if it's not minus infinity, then the topological free entropy dimension must be n. And for the n-tuples I discussed before, namely for the semicircular n-tuple, or for the universal n-tuple of self-adjoint contractions, T1, Tn, the topological free entropy the topological free entropy dimensions are equal, and they are equal with their free entropy dimension capacities. And here are now some of the big questions. Like there's a question with whether the free entropy, the topological free entropy is equal to the free capacity. Here you have the following question: if this topological, if this free entropy dimension capacity is equal to the topological free entropy dimension, are they equal in general? How there are partial results, but how far does that go? Is it a quite general thing? And of course, like what one dreams is with usual free entropy, that the free entropy dimension should be generator independent, so that it should become, you take an n-tuple in a von Neumann algebra, it generates the von Neumann algebra, and you'd like that if you look at this free entropy dimension, you should get something which is an invariant of the von Neumann algebra, which should not depend on the von Neumann algebra. So same question for C-star algebras. If I have a choice of Hermitian generators, is it generator independent? Open question. There are small partial results. Now, I would like to add a question about which I haven't thought too much, but which I think it's appropriate to ask. About free entropy, the usual free entropy dimension. While there is we don't know the answer to the general question whether it's the free entropy dimension is generator independent. There are very interesting things with a strongly one-bounded notion of strongly one-bounded von Neumann algebras of Kenley-Jung. And in that case, that's something which is related to free entropy dimension 1, but it's something which occurs is generator independent. If you have this strong one-boundedness property of Kenley-Jung, for one generator, then you can change the generator, it gets the same result. And there is an obvious question whether one can play the same game with norm microstates, and whether there is such, I don't know whether there is such a notion of strongly one-bounded C-star algebra, which in the sense of norm microstates, and that's a situation which is generator independent. I think it's a natural question. I should mention also that there are several results on evaluating the topological free entropy dimension, and on question 2, obtained by Don Hadwin, Junhao Shen, and their co-workers. And I want to show you a few results which don't require additional technical definition, some of the simplest results. And there are situations where one knows that, for instance, the topological free entropy dimension is generator independent, some of the simplest cases. Namely, here is, for instance, this. If I have A1, AN is a generator of a finite dimensional C-star algebra A, what is the free entropy dimension of A1, AN? And the answer they found is that it's just 1 minus 1 over the dimension of the C-star algebra. And of course, this does not the formula as such shows that it does not depend on the choice of the generator. Another situation we have is you take the full free product of algebras A1, AN, yeah? And the A1, AN are commutative algebras, the continuous functions on some compact subsets in R. So they are C-star algebras of with generator one element, and it takes a full free product. So that's a universal C-star algebra generated by A1, AN. It's the C-star algebra, so that every other C-star algebra generated by algebras isomorphic to A1, AN is a quotient of it. Then they found that, so if you want, you can say also, so it's a C-star algebra, like that was a universal contraction. Here you have the universal C-star algebra generated by an n-tuple of Hermitian of self-adjoint elements with spectra K1, Kn. And then the topological free entropy dimension is n minus the sum of 1 over the cardinals of Ki. So if the Ki's are infinite, you see these cardinals, infinite sets, cardinals are infinite, so 1 over this gives a 0. We have also other results I'm not going to detail, for instance, about what happens with topological free entropy dimension if you have direct sums, and many other results. So I refer you to their paper. So this is what I wanted to tell you. Thank you for listening.